we were reduced to the situation where the map from other way around, from X to A, which I usually call A. So this is the Albanese map, but it could be probably almost any map to an abelian variety works. We reduced to the case where this is generically finite. And surjective. And in particular, so the dimension of X is equal to the dimension of A. Now, what we had is we had some component, irreducible component, so it's of the form P plus T, contained in V0 omega X. So this is a torsion element of A hat, and this is a subtorus. And we knew that the dimension of Z is positive. Now, what our goal was, what we want is a point P prime in A hat and a subvariety T prime contained in T with dimension of T prime greater than 0 and let me set it up this way. P prime plus T prime contained in V0 omega X and minus P prime plus T prime contained in P plus T. So why do we want these two facts at the same time? Remember, that's what allowed us to get the contradiction to P2 equals 1. Once you have something like this, you consider the linear series Kx plus P prime plus alpha times Kx plus, minus P prime minus alpha to 2Kx, where alpha is in T prime. And when you look at this, this tells you that the dimension of 2Kx is greater or equal to 1, which is your contradiction because we know that P2 of X is equal to 1, right? Because, again, if this P plus T is also contained in V0 of omega X, so for any such alpha, we have a divisor in here and a divisor in here. We add them together, we get a divisor in here. And since this is zero dimensional, right, it cannot be zero dimensional because these two divisors vary. Okay, so that was the goal. And I did all of this. I just forgot what I needed to do to observe that the dimension of T prime is greater than 0. And it was actually really straightforward, so I should have just observed it. But let me just set up the diagram and do it over. So, okay, so it's not too hard. Let's do it right now. So think of this T. This T is contained in A hat, and therefore I have a dual map. I can take the dual of A hat, which is A, and I can map it to S, which is the letter I use to denote the dual abelian variety to T. So this map is due to that inclusion, and last time I called this map pi. Then I have my map X to A, and this is the composition. Maybe I'll give a name to the composition, F. Okay, so now I know that, let me consider, so I think K was the codimension of Z in A hat. Why is this an interesting number? Because if you have a component of codimension Z, then that tells you that, in fact, Z is also a component of Vk of omega X. Okay, so now I compute so I know that the cohomology group hk, this is by definition of vk, of omega x plus p plus, so I would like to view the elements in T as, so T is the same as the dual to S. I would like to view them as pullback of topologically trivial line bundles on S. So plus P plus F upper star of some element alpha. Okay? So this, by Collat's theorem, is the direct sum of h k minus j j f lower star omega x tensor p tensor alpha. So this is Collat's theorem plus the projection formula to take the alpha out. Okay, but by generic vanishing, so we know that all of these sheaves are generic vanishing sheaves on S. So by generic vanishing, this is the same as H0 K F lower star of omega x tensor P, tensor alpha. Right, because for all the higher cohomology groups, for general value of alpha, okay, I should say alpha in S hat some general element. So if I choose alpha general, then higher cohomologies of any one of these vanish. So the only one that survives is the zeroth cohomology. Okay, so now this tells me in particular that Rk F lower star of omega x tensor P is non-zero. If a cohomology group of something is non-zero, then the sheaf has to be non-zero. Alpha is in S hat. So S hat, it's a topologically trivial line bundle on S. And S hat is isomorphic to T. Okay, so I know that this group is non-zero. Okay, so this tells me that let's denote by F the general fiber of this map. And I'm going to pretend that this map has connected fibers. If it doesn't, I just need to consider the Stein factorization, but I don't want to introduce extra notation. So let me just pretend that it has connected fibers. So this tells me that hk of omega f tensor p restricted to f is non-zero, right? Because this is a torsion-free sheaf, and the generic value, let's call it, of the sheaf is exactly this number. Okay, but now you see the dimension of f is k, by the way I've set up things. That's just because x2a is generically finite. So this cohomology group here is the same as H0 of, by said duality, of P restricted to F dual. So this is a topologically trivial line bundle with a section. So this tells me that P restricted to F dual is O of F. And hence, it tells me that P restricted to F, no dual, is also equal to O of F. I mean, that's just silly, but now I'm sort of going to reverse the situation. So that tells me that K F lower star of omega x tensor P dual is non-zero. Right, so I guess these were all if and only ifs. So I get that this is non-zero. Okay, so then this tells me that V0 of Rk F lower star of omega x tensor P dual is non-empty. Okay? Now, I want a little bit more. I don't want it just to be non-empty. I want it to contain a component of dimension at least 1. That component will be my T prime, right? So this is, I'm going to deduce from the non-emptiness of this locus, that's what's going to give me this component T prime. So in order to get a T prime of positive dimension, I want to deduce that this is not 0 dimensional.
I'm sorry, I'm stupid. H0 of R, K floors R, omega is P2 O. How come it's not? Wait a minute.
How come this is non-empty?
Yeah.
Okay, because this is a generic vanishing sheaf, right? And that's the fancy non-vanishing for generic vanishing sheaves. So V0, you know that V0 contains V1, contains V2. If this is empty, they're all empty, which means that the Fourier-Mukai transform is 0, which means that the sheaf is 0.
I always
Okay, so what I want to show here is, the claim is, maybe I'll write it over here, claim is that the dimension of this V0, K, F low star, omega x, tensor P dual, is non-zero. So that's the thing I forgot to do last time. So how does the proof go? If, let's say, alpha in V0 of the same thing is an isolated point, then by the same argument that allowed me to deduce that Z was also a component of Vk, right? Now, an isolated point has codimension equal to the dimension of S. Then I know that alpha is a point of V dimension of S of the same sheaf. Okay. Now, by this argument on the top line, that tells me that HK plus dimension of S of what? Omega x plus P dual plus F upper star of alpha is non-zero. Right? Because here I have something in H dimension of S are K F lower star of that sheaf, and it's just a summand of that thing. Okay, but you see, this is the same as the dimension of X. So by set duality, this is the same as H0 of P plus F upper star alpha dual. So the only way that this can have a section is that if this is trivial. So that would mean that P plus F upper star alpha dual is O of X. But I had just assumed that somewhere that O of X was not a point in here. Right? So it cannot be of the form P plus some alpha. So that's impossible. Contradiction. Okay, so there exists a component, let's say T prime plus P dual. Let me just not be economical, plus alpha. So this alpha is some element of T, and T prime is contained in T, and this is a component of V0 K F low star omega x tensor P dual. Okay. But then, by that argument, this is contained in Vk omega x tensor P dual. every time that this cohomology group doesn't vanish, then this doesn't vanish because they're summons, one of the other. But now, since this is a generic vanishing sheaf, this is contained in V0 of omega x tensor P dual. Okay, so if I set it up this way, I do not need this P dual here. Because I'm keeping it there. Okay, so that does what I want. Right, so this P prime, I guess, is going to be P plus the alpha that I selected. And say alpha is in T, and T prime is a subtorus of T, so you see easily that these conditions are satisfied. Okay, so it was just this claim that I didn't do last time. I apologize for that. So any questions about this or something I did last time before I move on to characteristic P?
No.
Other questions? Okay, happy to move on to characteristic P. Okay, so sort of one of the themes I've tried to emphasize is that this Kolar vanishing, which is stronger than Kawamata-Vivek vanishing, sort of implies the generic vanishing results. However, it is well known, so in this form I think it's due to Mukai, for any prime number and any integer n greater or equal to 2, there exists a smooth variety x over an algebraically closed field of characteristic P, where the dimension of x is n, and L an ample line bundle such that higher cohomologies of, in fact, I think you can take H1 of omega x tensor L is equal to 0. Right, so you sort of have counterexamples to, in fact, Kodaira vanishing in any dimension for any characteristic. Yes. It wouldn't be very interesting otherwise, exactly. Thank you. Yeah. So you have counterexamples. So consequently, we expect similar counterexamples to generic vanishing. So I would like to, the next thing I'd like to do is give you an idea of why this expectation comes true. So maybe I'll state it as a theorem. So there's a published version which is not quite as broad as this. Which is due to myself and Kovac. And then I have a student trying to do it. So we find a counterexample in one specific dimension. And it's slightly not nice because there's some higher direct image that is creating the problem. You see in a second what I mean. So I'm having a student of mine actually sort of get the optimal counterexamples, write down the optimal counterexample. So for every prime, for every n, there exists a smooth variety. Okay, so I should write it. For every p and n greater or equal to 2, there exists x smooth projective variety over k equals k bar, characteristic k is equal to 2 to p, dimension of x is equal to m. And a generically finite map, A from x to A, finite map to abelian variety such that if I compute RS hat of A lower star of omega x, this is not the same as G S hat of A lower star of omega x. So we're expecting that this should be, I've done it the wrong way, RS hat of the dual on A of this guy is not the same as R0's hat of the dual on A of this guy. Okay. So it's very nice that this map is finite, so there are no high direct images to worry about it. So you don't have to worry, okay, is this failure coming from the high direct images, or is it really something that, you know, generic vanishing is really failing in any imaginable sense. So you could, instead of going from A times A hat, pushing forward to A, you could do a similar thing, pull back the Poincare line bundle from here to X cross A hat, and then push down to A. And you say, okay, so maybe this push forward doesn't have the right vanishing, but maybe the push forward from here has the right vanishing. Well, if the map is finite, there are no higher direct images from here to here, so those two things are the same. There is no uncertainty in the picture. Okay. So instead, in the counterexample, which is in print, the one with Shandor, the counterexample we construct, essentially, we make sure that the map from X to A has a higher direct image for omega X, and that's what causes the failure of generic vanishing. Okay, so I'm just claiming that one can make a much cleaner set of counterexamples. Okay, so let me try and give you an idea. So the idea should be you start with any counterexample provided by Mukai, and you construct one of these counterexamples. So we start with, let's say, a surface for simplicity, a surface. So X and an ample line bundle such that H1 of omega X tensor L is not 0. And you immediately have a problem, you know, maybe the Albanese variety of X is trivial. And so there is no interesting question about generic vanishing to worry about. Right? Okay, so what we want to do is we want to take an example with trivial Albanese variety, and we want to modify it to have non-trivial Albanese variety. Okay, so what I'm going to do is I'm going to consider two projections, two generic projections. I'll explain it in a second. The two generic projections. So you think of X as being embedded in projective space by some sufficiently ample line bundle, and you keep projecting until eventually you get the projection from X to P2. As long as you project from points outside of X, you get a morphism, and in fact, you can guarantee by picking your points generically that this will give you a finite map. Of course, it's going to be ramified, and the ramification locus may be quite ugly, right? Okay. Now, I pick my favorite abelian surface, and I do the same thing. I find the projection to P2. Okay, and so what I would like to do is I would like to consider X prime to be the product of these two guys. But a priori, this X prime may be quite ugly, right? But I make two observations. So maybe let's give these maps two different names, F and G. So first of all, I can assume that the branch locus of F intersects the branch locus of G transversely. Right, so the branch locus of F may have many singularities, but generically, so at every codimension, the singularities are codimension 2 points in P2, and if I move these around by some element in PGL2, then I can make sure that it intersects the other branch locus transversely. Right, so both branch loci could be singular, but at least their intersection is transverse. Okay, so also I can arrange things such that the degree of F and the degree of G are co-prime to P. This is not completely obvious, right? So essentially what you want to do is you want to check that in Mukai's counterexamples, your variety X, your surface X, admits a very ample line bundle of degree co-prime with P. And then you want to find a surface with the same thing, but take a principally polarized surface and take for your polarization a multiple of the theta divisor, which is co-prime with P, and that does it. Okay, so now when you do this, you can check that X prime will tend to be smooth, and that this map A prime will be finite, and this cover is separable of degree co-prime with P, and so in particular, H0 of omega X prime plus L prime will also be non-zero, where L prime is, I don't know what to call this, H upper star of L. Right, because this, one of the summons of this is H0 of omega X times L. Right, so this contains as a summand H0 of omega X plus L, and so it has to be non-zero. Okay.
It means H1 of X equals prime? Yeah.
Yes, of course I mean H1. This one will probably also not vanish, but I'm not interested in that. This, yes, of course, thank you. That's not exactly what I want, right? What I want is the generic vanishing condition, which, let me remind you, is something like this. I want H, maybe I want to forget about this, so now, from now on, replace X L by X prime L prime, and assume that we have a map from X to an abelian surface, a finite map. Okay, so we do have that H1 of Kx plus L is non-zero, but what we want is H1 of Kx plus, let's say, A upper star M H hat dual is equal to, well, one or the other, doesn't matter, A lower star, Kx plus MH hat dual. We want that this group is zero. There are no higher direct images, so these two are the same thing. For any H ample on a hat, and for any M sufficiently big. So that's my goal, is assuming that I have no vanishing of Kx plus some ample line bundle, I want to show that I also have no vanishing of Kx plus this thing here, which I'm thinking of essentially as epsilon times the pullback for an ample line bundle downstairs. So somehow this L, the inspiration is that this L, for M sufficiently big, this L is more positive than this. In order to make that precise, you have to take some a tau cover array, right? Because this is a vector bundle. So if I want to compare a vector bundle with a line bundle, it's probably nice to take my isogeny, split this as a direct sum of line bundles, and then compare. So I'll do that.
What is image hat?
Sorry?
What is image
Hat. Okay, so that was a situation when we have a,
Sorry.
no problem, a times a hat, and on a hat we have mh is ample on a hat, and then we define mh hat, and this is Mukai's original notation, is going to be rs, in this case, well, rs of mh, which since all high homologies of mh vanish is actually 0 s of mh. It's a vector bundle of rank h0 of mh, and it has the property that if, so we've used this already, but I'll use it again, so I might as well remind you. So fmh defines an isogeny from a hat to a, so I can, this is a vector bundle on a now, so I could do phi mh alpha star of this mh hat dual, and this turns out to be equal to a direct sum of h0 mh copies of the line bundle mh. So after this finite isogeny, it splits as a direct sum of ample line. Yes.
Sorry. I have a question about the beginning. You're saying like this generic vanishing can be derived by using Mukai plus polar vanishing.
Right.
That was the beginning. So now.
So in characteristic P, polar vanishing fails.
Yeah, but then we use the polar vanishing somewhere in the proof. But now you're using this failure of the Kodaira vanishing on X. So why?
So the map is finite.
Yeah.
Polar vanishing is going to reduce to Kodaira vanishing precisely because of this fact here.
Oh.
Well, okay, close to Kodaira, like pullback of ample, so maybe to some Kawamata vanishing.
Oh, I see.
Right. So we don't have high direct images to worry about. So
and that's what you were saying at the beginning.
Yeah. Okay, so what I'm going to do in this situation is I want to consider this isogeny from a hat, the h. Now this is also, I can pick things, say that A was principally polarized, and H is my principal polarization, and M is coprime with P, then I can arrange for this map to be a separable map. And then let me take a hat, X hat to be the fiber product. So not only is separable, but the trace splits, so that homology computations become particularly easy. Okay, so now instead of computing these groups, I'm going to compute hi kx hat plus this a hat alpha star bmh alpha star mh hat dual. So I'm going to be slightly cavalier here. This homology group is not equal to that homology group. This is the summand of this homology group. So, the contradiction I'm looking for is to show that this group doesn't vanish. If I show that this group doesn't vanish, that does not necessarily imply that this group doesn't vanish. Showing that this group doesn't vanish does not necessarily imply that this group doesn't vanish.
I thought you wanted to show this vanishes.
Well, then I would have that generic vanishing holds.
Okay, so maybe I want that this doesn't vanish, right? For generic vanishing, you want it to hold. Okay, so you see this group here is a direct sum of H, or let's just look at H1 of Kx plus A alpha star M H hat dual tensor Pi, where Pi are topologically trivial line bundles. They are in the kernel of this map from A hat to A, of this VMH, right? That's, if I push for the structure sheaf of A hat, these are the summons I get, right? So, okay, so these, if I show that this doesn't vanish, then I'm showing that one of these doesn't vanish. These all look an awful lot like this. They're just this guy twisted by a topologically trivial line bundle. So I can, with some work, I can make it into a proof. Okay, so what I'm saying is that this cohomology group is closely related to that. And the advantage of doing it this way is that when I look at this guy here, this is a direct sum of MH, of copies of NH, right? So now I'm down to computing a cohomology group of a line bundle. Now, if L let me just say it's another computation. Let's say for M sufficiently big, we fix RL, we will have that L hat, the pullback of L to X hat, minus MH is ample. Okay, so
what is L?
sorry?
What is L?
Okay, so I had an original line bundle L on X, which was ample. Then I pull it back here, I have L prime on X prime, which is ample. Finite map, again, L hat on this is ample. Okay, so now, the fact that you check on Abelian varieties quite easily is that if you have any ample line bundle on A, after I pull it back, any ample line bundle on A, after I pull it back by this isogeny, for M sufficiently big, the difference, that line bundle minus MH, will be ample. Since L is ample upstairs, I can assume that L prime minus the pullback of any ample, of a small ample, is ample upstairs, and I can deduce that result. So that's a basic result about abelian varieties. So this follows easily because if what's another? If G is ample on A, then B H alpha star of G minus MH is ample for every M sufficient. So in a certain sense, you know, if the feeling of this kind of computation is if H were a principal polarization, then there's on a hat, there's also principal polarization on A. When I pull back the principal polarization, it becomes M squared times the principal polarization. So it grows quadratically in M, whereas the polarization corresponding to MH hat is growing linearly with M, so it's going to lose out eventually. So if you played around with line bundles and abelian varieties and their duals, this should not be surprising. Okay, so then you do some covering trick. After a covering trick, it's not obvious that you can make this to be as ample as you want. You can make this to be very ample. Well, after a curving trick, I may pick a smooth curve C in L hat minus MH, the smooth curve.
I'm a little bit confused. Where am I? L hat minus MH? L hat
Okay,
is
so technically A hat upper star.
oh, sorry about that.
No problem. So MH is on here, L hat is up there.
Okay.
So then you can't assume that it's very ample, but you can use these curving tricks to then assume that you have a smooth curve in that linear series. And now you're going to look at this short exact sequence, 0 to omega x hat, A hat upper star, MH to omega x hat, L hat to omega C, A hat upper star, MH restricted to C to 0.
I'm sorry, Bldg. I'm a A.
No problem.
But because if G is upon A, but then how are we applying it? L
Okay,
hat was
So
what is G?
G is any ample line bundle on A
Oh,
for M sufficiently big will beat the other guy.
oh, I see.
So then you can certainly assume
I
that
see. Okay,
L
now
hat
I understand.
minus G, A hat upper star G is ample on X prime, and then you run.
I see. Sorry.
Okay, so now the whole point of picking C in here is that I can consider this short exact sequence. So omega C is given by omega x hat plus C, and so you're left over with this AMH restricted to C. H1 of this is 0 because the direct vanishing certainly holds on a curve in dimension 1. That's fine. So then you have H1 of this guy, which is non-zero, mapping to something 0. So H1 of this guy must surject onto a non-zero group. So that one is also non-zero. And so you violated the generic vanishing condition. As long as you can take care of all the little details that I mentioned. From this point of view, generic vanishing is completely hopeless. Anytime that you have a counterexample to Kodara vanishing, you can cook up a counterexample to generic vanishing. So you might say, just throw your hands in the air. The situation is hopeless. There is no chance. But of course, most of you know that there are some situations when at least Kodara vanishing holds. So you could hope that if x lifts to W to the second bit vectors, so if you have a sort of a first order lifting of your characteristic P variety, then generic vanishing holds. So in general, this is sort of, again, probably a bit hopeless because the Bellini-Lucy vanishing tells us that higher homologies of Kx under this lifting hypothesis vanish for every I greater than 0, L ample and X smooth. So it's a good substitute for Kodara vanishing, but even Kawamata-Liebig vanishing is not known to hold in this context, unless you assume some stronger liftability condition, except for surfaces. So if the dimension of x is equal to 2, then Kawamata-Bldg vanishing is okay. That's a particular situation. And so you can
so you, sorry, you were saying like even if x is liftable to W2, Kawamata-Bldg fails.
right. In dimension greater or equal to 3. In dimension 2, it's still okay.
So it's not, so you can expect polar vanishing to hold.
You cannot expect it. Well, okay, I think the jury is still out, but it's not really expected to hold.
But I thought polar vanishing is generalization of Kawamata-Bldg.
Right, so I have to admit, I do not know of any counterexamples to Kawamata-Bldg vanishing. So the place where you're using that L example is you want to know that HI, if I remember correctly, to the M, or maybe to the P to the E is equal to 0, some high enough multiple. So here you use vanishing. Now, on the surface, if L is big enough, you still have this kind of vanishing. But on a threefold, you don't have that kind of vanishing. That one is going to fail. I can show that that one fails. Doesn't mean that then the linear Lucy has to fail.
Oh, I see.
My guess is just all it means is that nobody has looked hard enough for a counterexample.
I see.
But I don't know. I really would not expect collab vanishing to hold, but
So didn't you say Kawamata-Bldg vanishing fails, or
it's not known to hold.
it's
That's the correct
okay.
statement.
Okay. I see.
Maybe I don't know of the counterexample.
No. I just want to know.
In dimension 2, it's okay, and so generic vanishing is also okay in dimension 2 for characteristic P over an algebraic closed field, and this is by my student Wen. So, and there are some results. So, Pink and Rossler use this lifting hypothesis to show that in arbitrary dimension, if A is ordinary, they show that the loci bi omega x, even in characteristic P, torsion translates of tori. So I'm not, if I have time, which maybe I will, I'll give you a slight hint of how this happens.
Wait a
I'm not
minute.
going to say anything now.
I'm sorry. So when you say generic vanishing holds for dimension x is equal to
Okay,
2,
so generic vanishing means R S hat dA A low star of omega x is equal to R 0 S hat dA A low star of omega x. It's the dimension statement.
A is Albanese map.
A is the Albanese. It's the dimension of these guys statements, right? Because we saw that this kind of statement is equivalent to codimension of each BI greater or equal to I. So that's just a pure dimension statement. And that statement is the one that they just showed fails in general. When it lists W2, we don't know in high dimension. However, Pink and Rossler show that the linearity holds at least when the Albanese variety is ordinary. And I'm going to leave that statement as is for now. I'll come back to it if I have time, because I need to set up some technicalities to give you an idea why something like that should hold. So I'm not really interested in the lifting to W2 case. I'm interested in the general case. So I want to set things up in such a way where I cannot recover the traditional generic vanishing. It fails, but I want to recover a substitute that's almost as good as generic vanishing. So the odds are stacked up against us, but I'm going to use the theory of F singularities to get something. So how does the theory of F singularities work? I consider F from X to X this is the identity on topological spaces, but if you have a function, then it gets pulled back to the p power of that function. Okay? So on functions, it takes a function to its p power, but the closed points get sent to themselves. Okay. Now I can use growth individuality to compare. So I can look at hom from omega x to omega x. I'm thinking of x as a smooth projective variety, and I can look at the space of homomorphism from omega x to omega x. In particular, there's a nice element in here, which is the identity, and I can push this forward. So I'm viewing that space as lying on here, and I push it forward by the Frobenius map. Now, growth individuality, the Frobenius map is a finite map. I don't have to worry about high direct images. Growth individuality tells me that this is the same as hom f low star of omega x into omega x. So, corresponding to the identity, I get the map phi, let's put phi1, from f low star of omega x to omega x. We call it a trace map. Now, I can iterate this procedure, so I can get maps and I'll call this iteration FE. Right, so here I have f squared low star of omega x. So I have a map from f low star of omega x to omega x. I push this forward one more time, and I get a map from f squared low star of omega x to f low star of omega x. And keep repeating that, you get this composition. Okay, so now if x is smooth, one can actually write this map down in local coordinates, and you can check that PE is surjective. However, typically it's non-split. You only expect it to be split maybe if x is fine or something like that. Typically it's very far from being split. This map is also interesting when x is singular. Think of defining it on the, if it's a normal variety, think of defining it on the smooth locus, and then just extending the map on the smooth locus to everywhere, because these will be reflected sheaves. And then when the singular locus is, it does something interesting. Maybe it's not surjective. So if x is singular, then we can think of the image, let me just call it phi e of fe plus star of omega x. This will be, this will contain pe plus 1, fe plus 1 plus star of omega x, and so on. So a priori, you get a descending chain of submodules of omega x, right? And this is worrisome because you expect that this descending chain may not stabilize. But in fact, by Hit theorem, I think this is due to gather, says that the intersection of these images is actually equal to phi E0 to 1, and hence to any one for any sufficiently big E. They all match. So it's a coherent sheaf, it's a subsheaf. Let me sort of think of it as omega x tensor sigma contained in omega x. So maybe I'm assuming that omega x, that it's Gorenstein. So omega x is a line bundle, so I don't have to worry about saying a submodule of omega x. I can just think of that as being tensored by some idea. Okay, so you would think of this sigma, this measures the singularities of x. Roughly speaking, it's the non-F-log canonical locus. So, if you were in characteristic 0, it should correspond to the non-log canonical locus. In characteristic P, almost. Not quite on the start with something in characteristic 0. For infinitely many p's, maybe this corresponds to the normal canonical locus. There is a dictionary like this, but it's a bit vague. So let me just call it, instead of, it's supposed to remind you of the log canonical locus, and I put the F in front of you to tell you that it's not exactly the same thing. It's just intuition. Okay, so now you can do this kind of procedure for not just for the canonical module, but for other kinds of modules. So, of course, we are mostly interested in a map from X to an abelian variety A. So here we could look at A lower star of omega X, and we could look at F lower star of A lower star of omega X. Well, you see, this is the same thing as A lower star, F lower star of omega X, because the Frobenius on X and A give you a commutative diagram. And so I had a map from this guy to that guy, so then I get a map between the push forwards. Okay, so let me call this map Phi1 again, right? So Gabber's theorem does not just apply to the canonical divisor. It also applies to objects like this. In general, it applies to any Cartier module. So this is an example of Cartier module, and Gabber's theorem applies to any Cartier module. So in this situation, S0, A lower star of omega X, is the stable image of Fe lower star, A lower star omega X to A lower star of omega X. So you almost feel like it should have been called an F0 because it's respect to the Frobenius map. I'm not sure whether the name S comes from. Does anybody know why it's called S0? Hello, stuff? One could think maybe it's because of Karen Smith, but I don't know. I doubt it. That was supposed to be a joke. Okay. Okay, so how does all of this tie in? Okay, so now I'm going to look. These are the guys that I was going to apply vanishing to.
Sorry, Chris.
Yes, go ahead.
I have a question going back to like 10 minutes ago. Sorry, like this,
Okay.
this W2 lifting claim. So you said if it, like lifts in the dimension of X is equal to 2, then counterphysic vanishing falls. So therefore, you can prove generic vanishing.
Right.
But so sort of like the original idea was so you have the vanishing, but then you prove some corresponding statement in characteristic P, and then you prove it. So is there any way that instead of saying, okay, we prove counterphysic and then generic vanishing, but you just have this family over.
So to deduce the result from characteristic algebraically from characteristic P to characteristic 0.
Yeah. So is there any corresponding?
So for example, this
statement?
result of Pink and Rossler. So it gets a little bit complicated. So it's not the case that if you start with a abelian variety characteristic 0 and you reduce it to characteristic P, that is going to be ordinary for infinitely many P. It's conjectured to be true, but it's a deep conjecture, it's not known. However, it's something a bit weaker is known. So instead of ordinary, I should have written no super singular factors, whatever that means. Now, being super singular is roughly the same as splitting as a product of non-ordinary elliptic curves up to some isogeny. It's a product of super singular elliptic curves. Now, this ordinarity conjecture is known in dimension 1 and 2, but most importantly in dimension 1. So the condition that they really need no super singular factors, if you're starting from reduction from characteristic 0, is true for infinitely many P. So then, for infinitely many p, your loci vi are torsion translated subtori, and with some work, you can show that that implies that the original loci in characteristic 0, vi, you kind of need some flatness to compare the two, right?
But I felt a little bit, like uneasy. In order to prove the vanishing, you use this family, but somehow instead of going through looking at the family, you were looking at the vanishing, only, and then prove the generic vanishing. I was wondering if you can carry out the argument to prove the generic vanishing.
So those examples definitely do not lift. So I start with something for which Kawamata-Bldg vanishing fails. Surfaces for which Kodaira vanishing fails. So they definitely don't lift. So there's
Just ignore me. Yeah. Sorry.
Yeah. So they yeah. Okay. So going back to this. Okay. So I've told you something pretty vague about the trace map for the canonical line bundle, and maybe some other Cartier modules, for example, the Cartier module you get by pushing forward omega x. Being a Cartier module just means that you have an OX to the 1/p linear map between the push forward and this. And Gabber's theorem applies in that situation. So now I want to do one computation. So I want to compute HI of the inverse limit of FE log star A log star of omega x twisted by some ample line bundle F. Okay? So, you should be immediately uneasy because this is a non-quasi-coherent sheet. Right? This is just an OX model. However, it satisfies the Mittag-Leffler condition, right? Because by this result of Gabber, the images of the trace maps stabilize. That's precisely the Mittag-Leffler condition.
What's that?
So the Mittag-Leffler condition, when you have a complex of modules, so an inverse system, it tells you that for every E, the image of ME plus K is inside of ME is fixed for K sufficiently big. Now, all of these kind of look like iterates of the same thing. So the only one you have to check is that the image in the last one is stabilizes in the coherent sheet. And that's what Gabber's theorem tells me. Okay? And this is a magical conditions for several things. It makes for example, the R1 of the inverse limit is 0 if it satisfies the Mittag-Leffler condition. And it then behaves well with respect to cohomology, right? Because if the R1 of the inverse limit was not 0, then there should be some kind of spectral sequence that would tell you that this should not be the same as what I'm going to write as the inverse limit of HI F E rho star A rho star omega x L. Right? Because, in other words, if it didn't satisfy the Mittag-Leffler condition, this limit and its limit in the derived category are not the same thing. Even though you start with a sequence of sheaves, I guess it's called the whole limit is not the same as the inverse limit. We're in a friendly situation. We don't need to worry about that. We can do, this easy computation. So now this is the same by the projection formula to the HI of FE log star A log star omega x tensor L to the P to the E. Right? Because the pullback via the Frobenius of L is L to the P. If I have the Frobenius E times, I get L to the P to the E. Okay. okay, but then this is the same as the inverse limit of each of these groups, for being as a finite map, is isomorphic to this cohomology group. I can forget about the F lower star. Right? I mean, the structure as a K vector space is changing, right? The one has multiplication is not by K, but by K to the P here, essentially. But as long as K is perfect, I've assumed it's algebraically closed, the dimension hasn't changed. And now look at these guys. These are 0 by Serre vanishing. As long as E is sufficiently big. So those vanish. Okay, so what's the upshot is, well, the upshot is that I have some very weak analog of Kodaira vanishing, or even of Kolar vanishing if you want, right? I get this vanishing of higher cohomology groups as long as I'm willing to consider this inverse limit.
You are now assuming that X is smooth? No.
Okay, so I don't actually have to assume that X is smooth. It's not necessary. In applications, because I get a bit nervous, but maybe it's true in higher generality, I assume that X is smooth, and this is the vanishing map. But regardless, even if you assume that X is smooth, this guy here is not locally free necessarily, so it's a non-trivial statement that the images of this stabilize. You have to really use the strength of Cartier modules. So I probably don't need to assume that X is smooth, but maybe that Kx is Q Cartier, and possibly its index is not divisible by P. Let's just say it's smooth, so I don't have to worry about it. Okay, so you may be tempted to say, we're just going to play the usual game, but we're going to replace the canonical line bundle, or push for the canonical bundle. You could do this for high direct images too, by this inverse limit, right? And so, why has nobody done this before? It's such an obvious idea. Well, okay, so people have tried, but it doesn't work so well, typically. So here's one instance where it does not work well. So you may say, after this computation, you get all excited, and you say, suppose that f from x to y is a birational map of smooth projective varieties, right? Then you might expect.
I'm sorry, Chris. Like a more primitive question. S0 L or star omega x. Where did it show in this argument?
Oh, okay. So S0 L star omega x is the stable image. It hasn't showed yet in this argument. The only thing that's shown is that there is a stable image. So saying that there's a stable image is the same as saying that this is mid-tag left. It's outside the mid-tag left.
Sorry.
I have not specifically used this guy. I will eventually.
Okay. Sorry.
Maybe not in today's lecture. But
this is the last lecture.
I know. So look at this birational map, right? So you may hope to show something like the inverse limit of f e lo star 1 ri a lo star of omega x is equal to 0 for any I greater than 0. That seems to be the analog of Riemann-Schneider. It's not known if this is true. It's true for cones, but otherwise it's not known. This is a conjecture. Now people have actually tried with some vigor to prove that, so it's not.
Oh wait, again, so you're expecting some generic vanishing involving f of e to whole?
Yes, so for now I just said I've observed that certain cohomology groups vanish.
Yes.
So, and I've said, okay, this is very much like Kolar vanishing. But then in the next graph I said, don't get too excited, because stuff that you might hope to be true is still not known to be true, even the most basic question. This is like, the most natural question is, okay, we don't have vanishing We certainly know that that fails.
Oh, I see.
I can write down counterexamples, but maybe counterexamples that are cones, but maybe the Frobenius stable version of Riemann-Schneider holds. Probably, it's a conjecture, but depending on my mood, I think that it's true or false, and I'm really not sure. Okay, so this is supposed to be a quotient.
But HI vanishing, yeah?
HI of this guy?
No. This HI of this
Yeah.
inverse limit.
Yeah, this is
vanishing.
correct. Yeah, that's correct.
But you're saying Riemann-Schneider version is not null.
It's not known to be true yet.
But usually, like if you have cohomology vanishing of Kodaira type, then the relative version would follow.
Right, but I would need, well, first of all, there's this inverse limit, which I, get a little bit worried about, but I would need a vanishing, not of the push forward twisted by ample, but I would need a vanishing upstairs with the pullback of an ample. Right, so this is like a mixture between
right,
Kolar
You're right,
and
yes,
Kodaira, but I really need a Kalamata Vivek vanish, which is not known.
Oh, I see.
Okay, so
So
I'm
they are,
supposed to take a break at a certain point. Should I take a break now and then? Yes, let's take a 10-minute break. You decide.
yes, please.
Okay, break.
Yeah.
Take a break and we'll.
So therefore, even with this Frobenius modification,
Okay, so
I feel like I have to somehow find a way to wrap the story up. So let me try and give you a precise statement. You might be waiting for it indefinitely. So, yeah, so here's the theorem that we were able to prove. So this is due to myself and those Patakapaldi. So let's suppose that let omega e plus 1 to omega e. We could work in general with an inverse system with certain properties. Okay, let's do that. Be an inverse system satisfying the Mittag-Laffer condition. And the property that higher homology groups of omega e tensor L hat dual are equal to 0 for every I greater than 0 and E sufficiently big.
so I know an abelian variety.
Yes. The inverse system of coherent sheets on an abelian variety. And this is an ample-line bundle, the dual abelian variety. I'm not going to write it down. Then, if I consider lambda to be the whole co-limit of RS hat dA of omega E, let me say a couple of words here. This is a coherent sheaf. Once I take the derived dual, it's no longer necessarily a sheaf, it's just an element of the bounded derived category with coherent homologies. When I take the Fourier-Mukai transform, again, it's an element of the bounded derived category with coherent homologies on the dual abelian variety. And now, when I have arrows from an inverse system, since I've taken the dual, it becomes a direct system in the derived category. So it wouldn't be appropriate to say take the direct limit. We take, so what you should think of the Hacon limit, you should think of this as the direct limit in the derived category, so some kind of derived direct limit. Right? So, in particular, this is not true for inverse limits because of issues like failure of Mittag-Leffler, but for direct limit, if I take the ith cohomology, it is the same thing as the usual direct limit as coherent sheaves of the ith cohomologies. Okay, so it's even though it's a derived category object, it's fairly friendly because it's a direct system. And so there's no statement here. This is just some element a priori. This is just some element in the bounded derived category of a hat with quasi-coherent cohomologies because of this direct limit. And actually, this is equal to H0 lambda, so it's actually a sheaf supported in degree 0. So this is the exact analog. If you didn't have this limit here, and you had, so
that's a statement.
That's a statement, yes. Right, so in characteristic 0, you remember the old statement was S hat, the A node star of omega x is equal to H0, so just write 0 S hat, the A node star of omega x. This was the characteristic 0 statement. Okay, so maybe there's one more statement I can make.
I have a stupid question.
Yes.
Where does that name come from?
Hacon limit?
Yeah. Homology.
Yes, I think it's a homology colimit. I don't
It's your
know exactly.
naming?
Sorry?
Is it your naming?
No. I pick up notes in the right category by Murphy, I think, or
Sorry.
Niemann, and I look for the results that I hope are true, and sometimes they are, sometimes they aren't, and the definitions.
Sorry.
So maybe in topology there are other similar things. I don't know.
I apologize.
So that's one, and the other property is, so if omega is the inverse limit of these omega e's, I don't have to say the derived inverse limit because they satisfy the Mittag-Leffler condition. So, and they're coherent sheaves, so the inverse limit is actually equal to the derived inverse limit. Then this is equal to -1 on a alpha star of how do I want to write it? Of the dual on A of the Fourier-Mackay transform of this quasi-coherent sheaf shifted IG. So that again is the same analog of the characteristic 0 statement, just you have this annoying inverse limit. Okay, so the proof of this is almost exactly the same. You need to know some technology about the right categories. You need to be able to deal with taking cohomologies of Hacon limits, knowing that is well defined, and
Wait, the same as what?
So for example,
the proof of this is the same
as the characteristic 0 proof.
But I thought we used the vanishing 0.
No. Remember, there were two statements. There was one statement: the following three properties are equivalent, and if a sheaf satisfies that property, we call it a generic vanishing sheaf. That was just a formal statement about sheaves and abelian variety. Now it became a formal statement about, essentially about Cartier modules. So a statement about Cartier modules is, so somehow Cartier modules are better behaved than canonical divisors. However, for every canonical divisor, you can make a Cartier module by looking for the statement. So that part of the proof is directly the same. Then, after you had that those three statements were equivalent, then you needed some Collar vanishing to get generic vanishing. So here we don't have three statements are equivalent. We sort of have two are equivalent. And in fact, we don't even have their equivalent, right? I have vanishing of high homology. So before I had 1 if and only if 2 if and only if 3. Here, what I've stated is that 1 implies 2. That's the only thing I've stated, and it's a much more complex statement. So what I'd like to convince, but at least this statement, okay, I have not proved for you in detail, but maybe I won't do it. At least that statement, I think, should apply to sheaves like this, right? I didn't exactly prove it because I'm supposed to show you vanishing, not twisted by an ample line bundle, but twisted by an L hat view. So I need to somehow, to get this kind of vanishing compared to that, I need to pass to this cover by this phi. So what I need to consider is this phi L from A hat to A, and I need to base change. And I will get the vanishing up here, but in order to relate the vanishing upstairs with the vanishing downstairs, it takes a bit more work because this map is typically inseparable, could be inseparable. So you need to be a bit more careful with how you phrase things. It's not too much harder, but there are some technical details. So the story is very similar, but there are several technical details because we're interacting technically. And you just have to be careful to make statements that make good logical sense, otherwise they almost always are false. If you don't care. Okay, so let me try and convince you that this is a useful statement, that we can get a lot of mileage out of it. So first thing is, I should try and convince you we should try and understand what does this guy here look like, right? So at least maybe for a general y, right? Because in the characteristic 0 case, when you did 0 s hat dA low star of omega x, then what this guy looked like was, let's see if I'm going to get it right. This guy looked like tensor ky. If I remember correctly, this y guy corresponded to, or there's a natural map to H0 A low star omega x dual. And so these guys here obtained with a direct limit of similar objects. So it should come as no surprise that this guy is given by the direct limit of H0 A low star omega E tensor Py dual. Right, so I'm iterating the same procedure many times, one for each E, and there's natural maps between these guys, so I get something like this. So of course, why is it the direct limit, right? So you have these maps, omega E to omega E minus 1, and so on. So you get maps of cohomology group from H0 of, there's no H star here, omega E to H0 omega E minus 1. So this is like an inverse system, and when you dualize it, it goes the other way, and it's a direct system. Just like the lambdas. Okay, so in our situation, omega E is just F E lower star of A lower star of omega x. And so let me state an easy corollary. Let's see what happens. Suppose that your usual locus, V0 of omega x, is empty, right? So from characteristic 0, we're expecting that this should not happen. That was my fancy non-vanishing, right? So I'd like to see some similar fancy non-vanishing pop up here. So suppose that this is empty. It should tell me that the variety is not of maximum Albanese dimension, for example. So let's assume it's empty and let's see where that takes us. Okay, so this means, or is equivalent to, H0 omega x tensor A upper star of P is equal to 0 for every P in X0 of A. Okay, very good. This cohomology group is the same as H0, A lower star of omega x tensor P. And so actually, this tells me that H0 F E lower star of A lower star of omega x tensor P is also equal to 0. Why is that? Because just like in the computation before, this is the same as H0 F E lower star A lower star omega x tensor P to the E. And so that's the same as H0 A lower star omega x tensor P to the E. And these are 0 for every P in pic 0 of A, and so P to the some power is still in pic 0 of A, so that's still 0. Okay, but then from this fact, I get that this implies, okay, so this fact is certainly wrong the way, oh, yeah, it's true, because lambda is equal to H0 of lambda, right? Saying that this is equal to that, in particular, is telling you this is a sheep in degree 0. Right? So remember, this is the same as H0 of lambda. Okay, so if these are 0, that's telling me that H0 of lambda, which is equal to lambda, is equal to 0. Okay, but then omega is equal to minus 1 A upper star dA Rs of 0 shifted by minus G. Whatever you do to 0, it's going to still be 0. It's 0. So what does that mean? Well, okay, so formally, it means just that this inverse limit of F E low star A low star of omega x, this is 0. But now, okay, so now it's not true that the inverse limit subjects onto A low star of omega x, right? I'd like to deduce that A low star of omega x was 0. That's what I would deduce in characteristic 0. But what I deduce here is just, if this is 0, its image in there is 0. So its image in there has a special name as 0, A low star of omega x. And what I'm deducing is that this is equal to 0. Okay? So now, okay, so for example, if, you know, it could happen, okay, I'll look for some fancy examples of this in a second. Let me tell you one case in which it's definitely not 0. So if x to A is generically finite onto its image, then there's an open subset on which then S0 A low star omega x is equal to A low star omega x, let's say restricted to U, where U contained in A of x is a dense open set. So maybe look at the set U over which this map is a tau. Okay. Let's assume that this map is separable onto its image. Then look at the dense open set where it's a tau, then this will be equal to that. So if you assume that this map is generically tau, then that has to general, you have to be a bit careful, right? Because if it's purely inseparable, then this map is factoring the Frobenius, so there's good reason to believe that it's also going to be non-zero, the image. Right? So, right, because the Frobenius from X to itself on the regular locus gives you an gives you a surjective map. So if the map is purely inseparable on an open subset, it should also give you a surjective map because it factors the surjective map given by the Frobenius. So I don't want to say that I really want to assume this map to be separable because it's not true. It's going to be nice in more generality. So you will have trouble when these fibers are not zero-dimensional, then something interesting could happen.
Would this prove that the basis of maximal one is a dimension? Then this eta and of general type, then mkx is birational, or
Okay, yeah, so I had a student of mine figure that out. He had to, if I remember correctly, he had to assume that the map is separable. So if it's maximal Albanese dimension, and I don't know if that was really essential, he assumed it. And Albanese map is separable, then I believe he was able to show that for any m greater or equal to 6, the 6th true canonical map is birational.
but there we only needed that non-vanishing statement.
Right. But it was, okay, so yes, you only needed a non-vanishing statement, but then you had to iterate it. You had to do it with this
IY.
Exactly. And so that IY and
have to vanish.
yes, so you have to
Here you don't have that.
well, okay, so we can set it up. So remember, I erased it. I told you that sigma, you can set it up. You can set it up. There is a way to think of some generalization of multiply ideals in positive characteristic test modules essentially, but it gets to be quite technical. So I would like to avoid that. But indeed,
but that's one application.
yes, but indeed it can be done, and so my student proves that if it's of genotype 6 times the canonical and separable, the evidence is separable, then 6 times the canonical is always birational. And I don't think anybody's been interested enough to try and see if you can remove the separable condition. I guess there's a limit to how much technicalities people want to worry about.
So this S0 Gaylor star omega x is the guy that you should look at.
Yes.
Whenever you have this
So
generic vanishing statement.
if this is non-zero, then you have a non-vanishing. Really of A low star of omega x above that guy too. The other thing that's becoming apparent is that the global sections that you really care about are the ones that give rise to this lambda. So the global sections that you really care about are in the image of this. So let me set that up. So you can, so we have this map from Fe low star of omega x to omega x, or with the push forward, but let me not carry that piece of information too. So I can take this map here and tensor it with omega x to the m minus 1, or any positive integer m. So then I get a map from Fe low star omega x to the power of 1 plus m minus 1 to the p to the e to f to omega x to the tensor n. Okay? And I denote H0 over E low star omega x to the 1 plus m minus 1 p to the E in H0 of omega x to the m for any E sufficiently big. Now, this is just a finite dimensional vector space over your field, and the images of this is a sort of decreasing sequence of subvector spaces. You don't need anything fancy to know that it's stabilized. They're just finite dimensional vector spaces, right? So it's clear that they stabilize for E sufficiently big. Okay, and so this is clearly, by the definition, a subspace of omega x dm. And somehow these are sort of the Frobenius stable sections, and they are better behaved than the overall sections.
Is this finitely generated?
I'll tell you the answer in a second. The answer is probably. I'll show you why. It's not. But maybe another thing I wanted to say is it's known, for example, that we don't have deformation invariance of all three genera in positive characteristics. So a natural question you could ask is maybe these sections are better behaved. Maybe you do have deformation invariance of three genera for these sections, not for the total.
Oh, so it's a fact that it fails? Like
Yes, there are counterexamples.
Oh. So where can I find it?
There's a paper by Su, which in Compositio, that gives counterexample even just for PG.
General type.
General type, yes, and there's the old example of Katsura Ueno from 1985 for surfaces of dimension 1, where for some low values, the three genera are not constant in fact. It's something about how you can have some wild fibers and they mess things up.
Characteristic P.
Characteristic P, yes. So, sorry?
But this guy,
Well, it's a question. So we know that these guys are not deformation invariant. These guys seem to be better behaved. Maybe these guys are deformation invariant.
oh no, I'm sorry, like I didn't understand the relation between Katsura Ueno example and Su's example.
Oh, so this guy shows that the first perigenera. So Katsura Ueno gave example of higher perigenera that are not deformation invariant for surfaces of dimension 1.
I see.
This guy here gives general type where the first perigenera is not deformation
I
invariant.
see.
And in characteristic 0, that's just Hodge theory that tells you that PG is deformation invariant. That's perigenera.
But yes.
So those are two troubling behaviors, but we don't really know what's going on. We don't really understand. Okay, so let me I'll answer your question in just 1 second, which is the thing I wanted to say next. But I wanted just to remark that these maps here, right, this omega E is a low star of omega x, so the section that corresponds to that, we're just twisting it by an extra p, right? So if I wanted, I could twist by another line bundle, for example, p here, I would have my p here, and here I would have a tensor p to the 1 plus m minus 1, p to the e. No, and you can do the same exact thing. It just depends how much notation you're willing to carry on. Okay, so let me try and answer your question. Are those things finally generated or not, and how far are they from H0 of omega x to the m? So let me do one example. E is an elliptic curve. Then E is ordinary, this is the definition, if and only if S0 of omega E is equal to H0 of omega E. This is a bit overdoing it. This is just one dimensional, right? So this thing here can either be 0 or the whole thing. It's super singular, it's 0, if it's ordinary, it's the whole thing. Which means that the section of the canonical line bundle, which is the same as the trivial line bundle, is Frobenius invariant. That's what it is. Okay, so now that tells you that you can take E times any variety, say y is of general type, and maybe you could assume that S0 of omega y is equal to, or omega y to the m is equal to H0 of omega y to the m for every m greater than 0, or you could assume that E is not ordinary. Then, the fact, so pluricanonical forms on here are just product of pluricanonical forms on E times pluricanonical forms on Y. So then, the upshot of this is that the codaric dimension of E times Y is the dimension of Y, so the dimension of the ambient is codimension 1, sort of the eta configuration, the fibers of E. However, you have that dimension of S0 of omega E times Y to the m is always 0. These are always empty. Okay, so this is a little bit troubling behavior. It makes you think that most of the time you won't have any sections in here. It won't be interesting. So let me try and make the counter argument. Let me try and say why most of the time you should have interesting sections. So let me define the ring corresponding to this. So I'll say S0 of x will be, let's call it S of x, will be the direct sum of S0 omega x to the m greater or equal to 0. This is clearly contained in the canonical ring, which is the direct sum of H0 omega x to the m. And it's easy to check that this is an ideal. So anytime you take a Frobenius invariant form and you multiply it by some pluricanonical form, you look at this and you use the projection formula, and it immediately tells you that their product is again in here. So it's an ideal. Now, so if this is finally generated, then this is going to be finally generated. Right? If this is Noetherian, that will be Noetherian. So we hope that this is Noetherian. So the conclusion should be that this is finally generated. But we don't know this yet. So for surfaces, for example, it's always finally generated. Another, from this observation, another thing that follows is that if S0, if S0 of omega y to the m is non-zero for some m, then essentially these two rings have the same size. So the transcendency degree of S of x over k minus 1 is the same as the transcendency degree of R of x over k minus 1. This is what we call the codaric dimension of x. And so this is what we'll call the stable codaric dimension of x, the Frobenius stable codaric dimension of x. They're the same number. So sort of, why do I need an extra name for it? It's sort of emphasizing that I'm looking at the Frobenius table, and as long as this is not minus 1, then it's the same number. It could happen that this is minus 1 and that's not. And the one thing that I also should mention is that if the codaric dimension of x is equal to the dimension of x, then the codaric dimension of x is equal to the stable codaric dimension of x. So this bad example that I had only happens when x is not of general type. I gave you something of codaric dimension n minus 1, for which these two numbers were not the same.
I see.
But in most cases, general type, they are always the same.
Is it finite, this extension?
From here to here?
Yeah.
Finite as modules, of course, no. Finite as algebras, yes.
Finite as algebra, yes.
Oh, okay. Assuming it's finally generated, then it has to be finite.
Yes. But So suppose you show Sx is finitely generated. How far are you from showing Rx
Ah!
is finitely
Okay,
generated?
that's not obvious to me. Yeah. That's, yeah, so if you knew that this is a finite extension of that,
Yeah.
then you would deduce, I don't know. I guess the answer is I don't know.
But isn't your hope sort of like finding the analog of the argument for Sx?
Yeah, we haven't got that far yet. yes, but
But
it's a good observation. That may be one, in certain situations, something you could hope to do, to show that this thing is finitely generated. It should imply that this thing is finitely generated, right? Because this is a finitely generated module over this. Well, I don't
Well,
know.
no,
Yeah.
no.
It's a module over that. So
you
we could hope that if this is finitely generated, it should
Yeah,
imply that.
still, like you have to show something.
Yeah, I think there is something to show.
But one step. I thought that was your hope.
Well, that's something that's been done before too, right? When improving existence of flips in Shortlove's original argument, he shows that some smaller subring of the canonical ring is finitely generated, and that the whole thing is just a finite extension, so that's finitely generated as well. So, yeah. One country. Okay, so these are the definitions, and so now that I have these definitions, I want to do two things. Maybe I'll state a theorem, which I won't prove, and then I'll actually tell you how this stuff is related to showing that these loci are abelian subvarieties. Well, Torsion translates to abelian subvarieties.
Aside from this generic vanishing line, so can you look at this S0 omega x from n somehow, or its analog, to carry out the analog of your extension theorem?
We're still very far from that, but I can tell you something.
Or maybe, do you expect some vanishing theorem to hold for this stable guy? Or I don't know what I'm saying.
Right. So there are things that you expect. There are things that are true. Let me give you one example of something that has nothing to do with generic vanishing, but might try to commit. So you have a fibration from X to Y. Traditionally, you want to show that the push forward of omega X over Y to the M should be positive in some sense, weakly positive. So if that's a curve, it should be net. This is false.
In characteristic P.
In characteristic P, of course. However, what's true is I'm gonna slightly lie. Okay, if you make some minor assumptions, it's for example, finite generation of that ring and these two rings are the same, something like that. It's true for something that looks like S0 at low star omega X over Y to the M. So there are some results due to Fatakfalvi and Ejiri that say things like if the fibers are ordinary, maybe ordinary means that these two rings are the same, something like that, and maybe finally generated on 5. So if the fibers are nice and the basis of general type, then CNM statement holds even in characteristic P. Okay, so it's still early days. We don't know exactly how nice the results will eventually be. If it's going to really get to a theory which is sort of as good as what we have in characteristic 0, or there'll still be a lot of mucking around. A lot of information is sort of arithmetic, right, in characteristic P. So maybe if you package the arithmetic input nicely, then you get some beautiful statements. Or maybe it's just not possible. I don't know. There's a lot of uncertainty.
I have another
Yes.
question. So, sorry, Chris. Is there a log version of this?
Yes. And you don't want me to write it down.
No.
But, well, actually, I can sort of tell you how to write it down. So, the log version looks something like this. You have fe log star omega x to omega x. You rewrite this as fe log star of omega x to the 1 minus p to the e to O of x. All I did is I tensored by omega x inverse. Now you consider your boundary, like if you have a pair xb, then you can look inside of here to fe log star omega x plus b to the power of 1 minus p to the e. Notice 1 minus p to the e is negative, right? So to go from here to here, I'm just adding b to the 1 minus p to the e.
Oh.
So that goes in here. I look at the image of this. The stable image is stable. It's a coherent subsheet. So the stable image, it will subject onto sigma of xb contained in there, which you are thinking, but it's not the same as the multiply ideal sheet of x and b. So maybe if you started with something with characteristic 0, and reduce mod p, maybe for infinitely many p, you could hope that these two are actually the same. And there are some results to that effect.
I mean, look, I thought, okay, that's good.
Okay, so maybe if xb is KLT in characteristic 0, then this will be trivial for infinitely many p. Or maybe OP is sufficiently big, I don't remember exactly. And maybe if it's log canonical, it's really complicated. It's equivalent to this ordinarity conjecture that if you start from something characteristic 0, so I didn't say that, but the expectation is that if I start from something in characteristic 0, for infinitely many p, these two rings are the same. So typical situation is that S of x is very big. Okay. Okay, I wanna state one theorem which I won't prove, and I wanna give you some idea about the linearity of these laws. Okay, so let me state the theorem. See if I can find it. Okay, theorem. If the stable quadratic dimension of x is 0, then the Albanese map is surjective. And if also the dimension of x is equal to the dimension of the Albanese, then A is the top. And A is ordinary. So this is the analog of Kawamata's theorem in characteristic 0 from 1979 in positive characteristics. So it doesn't work as a birational characterization for any abelian variety yet. I don't know if it fails or if it just doesn't work. But for ordinary abelian varieties, right? Ordinary abelian varieties are just abelian varieties such that the stable quadratic dimension is 0. For ordinary abelian varieties, there's a chronological characterization. So this is just to say that if you make these adjustments, some theorems do work with positive characteristics. And in the online version, I'm assuming that P does not divide the degree of A. Well, I believe that we managed to remove that condition, so that's why I did not write it. It's not published yet, though. So somehow, towards the end of the proof, there's some technical thing that we're bothered. What if P divides the degree of the Albanese map? You know, so the trace is not split. Once you know that it's a genetically finite map. But we think we've been able to remove that hypothesis. So that's one
I start from some abelian variety which is not ordinary, and then I take A hat. A hat has Kodaira dimension 0, so Kodaira dimension, stable Kodaira dimension must be also.
No, because if A is not ordinary, A hat is also not ordinary.
Oh, I see.
Yeah, so
Yeah, that's
this
right.
ordinary condition
That's right.
is preserved
Yes,
by
yes.
isogeny.
I
It's not even separate.
You're right. So it's the Kodaira dimension is the same as the dimension of X, only if it's not 0. S0 or something is not 0.
Correct.
I see. Sorry.
No problem. So the other theorem I want to mention is the following. So suppose that A theta is a principally polarized abelian variety, then and D is in M theta, then the pair A1 over M D is F pure, and the pair and theta itself, and if theta is normal, it is strongly irregular. So I haven't defined these notions. You should think of F pure as being the positive characteristic analog of log canonical, and you should think of strongly irregular as being the positive characteristic of Kawamata log terminal.
Do you have an effective version of the first theorem?
No.
No?
No, we have to do a whole big mess to prove it, so we're not even close to getting an effective version.
But this is a corresponding statement of Kawamata's.
This is corresponding to Kawamata's, not to the strengthening of myself
Sure.
and Alfred. So in particular, I believe, but I haven't checked, this should imply nice properties about the singularities of theta. Well, it certainly does imply nice properties, but I believe it implies in particular that they are, how do we call it, WK rational? In the notation of NO and Chagmatu moving. So this is something you want to know if you're trying to count the number of rational points on a singular variety. So it should have some nice sort of almost number theoretic applications. Okay, so I'm not going to say anything. Not going to say anything about the proof of that, but I do want to say a last couple of words about again about the Frobenius stable loci and about how that ties into the fact that the homological support loci are subtoral. Yes.
Sorry, about the first theorem. So I thought you told us that we should be thinking about the stable locus instead of the whole thing.
Yes.
And then how come I cannot say if P2 of S0 or P H0 or, like your statement, corresponding statement, why does it?
Well, I don't know. I just cannot prove it yet. My generic vanishing statement that I've now erased is something about inverse limits, so it's more complicated. So when I have a Kodaira dimension thing, sort of I understand all multiples somehow, and it's easier to take care of this inverse limit kind of situation.
Delicate.
Yeah, I'm not saying that one can't do it. I just haven't been able to do it yet. I'd love to do it. Okay, so exactly, but a lot of things are easier. So for example, we don't know that the loci V0 are Trojan translates of subtori, right? So what you do typically is, here's your Boolean variety. If there's a positive dimensional component, then you add it to itself the dimension of the variety plus 1 times, and they will cover the whole variety. So even if it's not a subtorus, by adding it with itself g plus 1 times, you'll get the subtorus. You'll get the smoothest abelian variety spanned by this. So that's one way that it's sort of harder to work with these, but you can get around it. You can get subtora just by saturating them. That's one way. But there's other technical issues about doing so. Okay, so what did I want to say? I wanted to say the following. My claim is, if S0 omega x tensor P is non-zero, then S0 omega x tensor P to the E, P to the P is non-zero. Okay, let me prove this. It's a exercise pretty much. So what does it mean that this is non-zero? So I look at H0 omega x tensor P. Then I have a map in it into here from H0 f log star omega x tensor P squared, P to the P, and H0 f log star omega x tensor P to the P squared, H0 f3 log star omega x tensor P to the P cubed. Thankfully, I ran out of Blackboard, but you can continue. And you're looking at the stable image of all of these. Now, okay, so forget about the last step, right? And notice that this is isomorphic to H0 of omega x tensor P to the P. Like this push forward is around here. I already applied the projection. Notice that this is isomorphic to H0 f lower star omega x tensor P to the P to the P. This one is H0 f lower star squared omega x tensor P to the P to the P squared. Okay, so if all of these maps are non-zero, then all of these maps here have to be non-zero. I can probably show that the dimension of these two spaces are the same as well, but this argument just shows that if this is non-zero, then the other one is. Okay, so now think of V0 of omega x as being contained in a hat. This is a closed subset with the property that if y belongs to V0 of omega x, then P times y belongs to V0 of omega x. No, I don't want to call it V0, the stable version of V0, right? The set of points for which this number is not zero. Okay, so there's a little issue. This may not be closed, so I need to take the closure of this. Let's not worry about that so much. So pretend that this is closed. Then you have subvarieties of a hat which are fixed under multiplication by P. Right? So you could guess that these subvarieties tend to be linear. And in fact, it's a theorem of Pink and Rossler that they are. So the theorem says if A has no, well in this case, a hat with no super singular factors, e.g. A is ordinary, then any subset, any closed subset Z contained in A, such that PZ is contained in Z, precisely, then yeah, any irreducible set, closed subset with this property is a torsion translate of an abelian subvariety.
What did you write there? I'm sorry, Michael. Y is inverse to omega x, then?
So if I have a point in here,
Yeah.
then p times y is also there. I'm switching from additive to multiplicative notation.
What is P?
P is
P is the curve.
over K, characteristic K is equal to P, or maybe K is equal to K bar, or at least perfect, I don't remember the exact assumption. And it's unfortunate that they insist on calling P the Poincaré line bundle the same as the connection.
Sorry, I see. Now I see the.
So I tried to make the prime number smaller than the line bundle.
I see. So that's a conclusion of the claim, consequence of the claim.
Yes.
Yeah.
The consequence of the claim says that this subset, I don't know that it's a closed subset, so I have to worry about that. The subset is closed under multiplication by P. Now, what Hacon says that any closed subset closed under multiplication by P is one of our friends, a torsion translate of an abelian subvariety. And so, if we're in the case of an ordinary abelian variety, then typically we expect to have tori. I mean, I can make this into a precise statement. I take the closure of this, I take any maximal dimensional component of the closure, it has to be a torsion translate of an abelian subvariety. And Pick and Rossler use this resulting characteristic P to deduce the resulting characteristic 0. That the loci V0 are union of torsion translates of abelian subvarieties. They start with characteristic 0, they reduce mod P. For infinitely many P, they show that A has no super single factors. Then they deduce that for infinitely many P, the loci are unions, finite unions of torsion translates of abelian subvarieties. And then they put that together to deduce a similar factor, the original variety characteristics. And so we do have something in characteristic P that we can use like that. It gives us some tool. It's still a bit of an uphill battle, and yeah, I don't know how well it's going to play out in the end. But we already have some nice results. So I think I will stop here, just take questions and full reflection.